Tick, tock, tick, tock. That's the sound of a clock. A second, another second, tick, tock, tick, tock. Your computer does the same thing. Every electronic device you own does the same thing. It knows how to keep a second, a millisecond, a microsecond, a nanosecond, a picosecond. The problem with superfast processors with lots of cores, or GPUs and AI accelerators with lots of chiplets, is that they need lots of fast, accurate timekeepers. Not everything is 100% accurate and jitter-free, but the technology we've been using for decades, Quartz, isn't up to the task. I'm not saying it's a stone that shatters, but it doesn't have the qualities we need to drive more frames, more tokens, or more efficiency. The industry is turning to MEMS, a silicon-based technology that takes timing into a new era. I've spoken about it here on the channel before, and I've interviewed executives who are pushing it forward. But what was never fully clear was the scale of how these machines keep timing to the picosecond. It may sound silly to those deep in the field, but I was given a chart of how computers keep time, and I want to go through it with you on the channel. So here's the chart I was given. At first glance, it might look like an ascending ladder of different timing devices, but this is really the roadmap of how timekeeping evolves inside electronics. At the very bottom, you see the resonator, the raw source of the frequency. Then we have oscillators, buffers, clock generators, jitter cleaners, all the way up to full network synchronizers and even a software layer. Each step exists because the step before it isn't enough on its own as we build more complex chips. Altogether, they show how you go from a single vibration to an entire infrastructure. Now, I'll be honest, I had to do a lot of research for this video, but I hope to take you through the key points at every stage of this ladder. Let's start at the bottom. At the bottom of the chart is the resonator, the raw element that defines frequency. Everything in electronics begins here. A resonator is simply a structure that naturally vibrates when energy is applied, and at the rate of vibration sets the reference for time. For almost a century, that job has been done by quartz. A crystal of quartz, cut to the right size and angle, will ring at a very precise frequency when you pass a small current through it. That's why they call it piezoelectric. That's why quartz watches can stay accurate to within seconds per month, and why the same principle has powered radios, microcontrollers, and computers since the early days of electronics. Quartz has been cheap, reliable, and good enough. There are a dozen companies who make them at super low cost. But let's be honest, it's also a piece of rock. It has to be mined, cut, polished, mounted in a package, and protected. It is fragile. It has lots of problems when it comes to the metrics that high-performance timing needs. For example, it doesn't tolerate shock well. Imagine your watch drifting by a few seconds with every step you take. It drifts with temperature. Imagine your PC frequency goes awry when you pile on the compute. It also doesn't integrate with the way we now build chips, taking up lots of space. For small devices like wearables or phones, quartz takes up that space. It also consumes power. To get the frequency out, a current needs to be applied. And that means for large systems like GPUs or servers, it can reduce the peak performance by taking part of that power budget. Beyond that, it also doesn't offer the robustness or programmability that modern designs demand. So this is where MEMS comes in. It stands for Micro Electromechanical Systems, and they're built in silicon. Instead of cutting a rock, you etch a structure that resonates at a frequency directly onto a wafer. The same way we make transistors. The result is a smaller but tougher design. Because they're small and not built from mined rocks, MEMS resonators can survive drops, vibration, and wide swings in temperature that would normally cause quartz to fail. Normally you'd pair a resonator with control circuitry, which gets you up the ladder in our diagram. But at this stage of the story, the resonator is just the vibrating element. On its own, it's not a computer or system clock, it's just a frequency output. But those raw metrics matter. The advantages of MEMS at this foundational level are what allow the rest of the timing ladder to even exist at all. It's at this point I should least talk about this video's sponsor, SciTime. They're the leading MEMS timing company on the planet, with some very big customers in large AI infrastructure, as well as consumer companies. SciTime in this instance started with oscillators, which we'll get into a second, but have proved that MEMS resonators can compete and surpass anything from the quartz industry, particularly when it comes to those metrics we mentioned earlier. Resonators alone, without the circuitry, is actually a $4 billion market, believe it or not. Once you have a resonator, the next step is to make it usable, and that is the role of the oscillator. An oscillator is the first complete timing product. The resonator plus the electronics that sustain the vibration, regulate it, and buffer the output into a clean clock that a system can trust. This is the point on the ladder where timing becomes a drop-in component on the board and shows up everywhere. On motherboards, in phones, in network switches, in industrial controllers, and in servers. From here, the landscape actually splits into 4 different families, each chosen for different constraints and all judged by a common set of values, such as accuracy in parts per billion, stability over temperature and shock, short-term phase noise and jitter, long-term aging, startup behavior, power size, and in some cases, programmability. The first is an XO and is the baseline crystal oscillator, even though it's a crystal and we're talking about a MEMS device. An XO is a fixed frequency oscillator that gives you a stable reference with low cost and low power. It's the workhorse you see stamped 25 MHz or 100 MHz on a PCB. Ideal for general digital clocks, microcontrollers, storage, and many peripheral domains where tight holdover is not required. Holdover in this context just means keeping the clock accurate without an external reference. After the XO, you have the TCXO, which adds temperature sensing and compensation so the output stays on target even as the device raises and falls in temperature. TC, in this instance, stands for temperature compensated. So it's a temperature compensated crystal oscillator. It trades a little power and cost for tighter stability across the full operating range, and that's why you see TCXOs in cellular radios, GPS receivers, IoT modules, and items that sleep and wake through wide temperature swings. Also edge devices that need predictable frequency across seasons and enclosures. So depending on the brand, you can also get what's called a super TCXO. SciTime calls their product the Elite RF, and there's quite an amusing story here. Even though it's a temperature compensated oscillator, they added really impressive low jitter performance as well for radio frequency devices. That's why it's called RF. But the jitter is so good, it got the attention of some of the AI accelerator companies. I really wanted them to rebrand it to Elite AI or something, but it's funny how a radio frequency design part seems to work for a GPU and the whole GPU infrastructure thing. Now third on our list of XOs is the VCXO, or voltage controlled crystal oscillator, and that adds a control input to the resonator. This allows the frequency to adjust within a defined range. The benefit is stability, ensuring that the frequency can adjust if there's a signal from a source that could be disturbed. This is why VCXOs sit at the heart of SerDes links, at the heart of Ethernet, broadcast and pro audio gear, storage, and why any design that must track an upstream clock without dropping frames or packets is key. The metrics here include how far the frequency range can be adjusted, how the frequency responds to voltage and if it's linear, and how well it isolates other electrical noise. Then also it has to return to center, i.e. how well it performs if there's no control input. That's a lot of words to say how far you can adjust the frequency, how smoothly it adjusts, and how noisy the adjustment is, but also how well it goes back to normal. The thing is, if you want high-speed networking, these qualities are a mandatory requirement. The fourth in our list of XOs is OCXO, or Oven Controlled Crystal Oscillator. That means putting it inside an oven. Now, that burns more power and it takes time to warm up, but it does deliver the most stable frequency regardless of the external environment or any aging effects. You find OCXOs mainly to anchor timing in base stations, or boundary clocks, grandmaster servers, test and management hardware, scientific instruments, and any rack that needs to keep 12 to 24 hours of time when those reference clocks disappear. These are the most expensive out of all the oscillators, and we have covered the latest from SciTime before, but these devices offer better power, better stability, and are smaller than any of the Quartz competition. The Epoch MEMS OCXO shrinks that oven into a package far smaller and far more power efficient than Quartz ever managed. This shift is why oven-controlled crystal oscillators, even though once exotic, are creeping into racks that previously made do with less. Overall, there are 4 or 5 different types of oscillators I've covered here, but SciTime say that they've apparently shipped 3.5 billion clocks since 2019, almost split equally between data center, industrial, and consumer. They're not marked separately on our diagram, but it just goes to show the variation in the market. I want to put this slide up because this is where the market is actually going. Resonators and oscillators are the biggest parts of the timing market, with a predicted $8 billion addressable market by 2027. So now you've got your resonator powering an oscillator that's generating a clean clock signal. The next challenge is how do you deliver that signal to the places that need it? That's the job of the buffer. A buffer takes one input clock and fans it out to many outputs, each one a faithful copy of the original. It sounds simple, but it isn't. Because modern systems have dozens of domains that all need clocking. A modern CPU, for example, might have a clock domain per core, per cache subslice, per integrated GPU slice, then another clock for the memory controllers, for the I/O, and whatever else is on the chip. If we're talking chiplets, then they keep adding up as the domains increase. The key is that each copy of the clock has to arrive with the same integrity as the original, without adding any of the bad metrics. Skew, the ability of a split clock to end up at different parts of the cycle, or jitter, the wobble in the clock, are two of the major concerns. If a buffer adds too much delay or wander, different domains drift apart, and at high speed, that can mean corrupted data or even a system failure. This is especially important in large servers and networking equipment, where a single oscillator's reference might need to be distributed across multiple boards or chips. For example, in a dual socket server, if one socket drifts even a fraction of a nanosecond off the other, cache coherence can break down. That's the kind of job that buffers are keeping in check. Buffers in those cases provide multiple low jitter outputs, often differential, so that every part of the system stays aligned. They can also include features like signal isolation to keep noise from one domain from feeding back into the other. From a metrics point of view, buffers are judged on skew, jitter, and fan-out capability. Designers look at how many copies they can make, how tightly aligned those outputs are, and how little extra noise is introduced along the way. And in some cases, power consumption and format flexibility are equally important. Now, buffers may not look as sophisticated as a OCXO or as programmable as a VCXO, but they're the glue that makes the clock trees possible. Without them, you couldn't take a single timing source and scale it across an entire system. But let's be realistic here, some systems don't want the same clock replicated 100 dozen times. Some systems need dozens of different clocks at different frequencies, all derived from the same reference. That's where clock generators come in. A clock generator takes a stable reference, often from an oscillator, and uses internal hardware to multiply, divide, or synthesize entirely new frequencies. That hardware is called a phased locked loop, and it's a way to multiply or divide clock frequencies or synchronize two parts of the system. The benefit is that you can create an entire clock tree from a single input. On a server motherboard, for example, one generator might provide 100 MHz for the CPU, 25 MHz for Ethernet, 48 MHz for USB, 125 MHz for PCIe, and 32 kHz for the real-time clock, all aligned to the same reference. That's why these devices are sometimes called clock synthesizers, as they don't just copy, they create. Now, the key value in a clock generator is integration. Instead of sourcing a separate oscillator for every domain, you can use one generator to drive them all. That cuts down on board space, reduces the number of oscillators that need to be stocked, and simplifies the design. It also improves coherence because each derived clock is mathematically linked to the same reference. But going back to the metrics that matter in this case, are often output jitter, phase noise, and frequency flexibility. Good generators deliver low additive jitter even when producing dozens of outputs. They support both integer and fractional frequency synthesis, so you can target exactly the value a protocol requires. They can output in different formats if needed, depending on if you're running in metric or imperial. Power consumption also matters, especially in mobile or embedded designs where clock generators may run continuously. In high-performance systems like GPUs or network ASICs, clock generators are essential. Each chiplet, for example, or each I/O block, each accelerator unit may need its own frequency domain, and they all have to stay locked with a common master. Without generators, designers would be relying on multiple discrete oscillators and buffers to cover every domain, which adds cost, board space, and design effort. The purpose of clock generators is to streamline that design and avoid that trade-off. Now, so far in this video, we've taken a single vibration and turned it into an oscillator, fanned it out with buffers, or multiplexed it with generators. But every time you move, split, or synthesize a clock, you add noise. That noise shows up as a function called jitter. And jitter just essentially means the tiny variations in when each clock edge arrives. At low speeds, you can often get away with jitter, but at gigahertz data rates, even a handful of picoseconds can mean the difference between clean data and corrupted bits. And that's why jitter cleaners are really important. A jitter cleaner, as the name suggests, takes a noisy reference and regenerates it as a clean, stable output. Inside a jitter cleaner is usually a high-quality phase-lock loop or a cascade of multiple PLLs. The cleaner locks onto the incoming signal, tracks the long-term frequency, and filters out the short-term jitter, producing a much cleaner signal on the other side. The metric that matters here is essentially jitter attenuation, basically how much noise the cleaner can strip out without adding any back in. And sometimes it adds some back in because nothing is 100% perfect here. A phase noise plot is often used to show performance, with a good cleaner reducing noise by tens of decibels across the frequency range. Yeah, this stuff uses decibels as metrics, and I don't want to make this video math heavy, but reduced decibels is good in this case. Two other metrics for jitter cleaners are lock range and holdover performance, basically how far it can track an incoming signal and how well it maintains stability if that signal disappears. Use cases for jitter cleaners are basically anywhere where data integrity is critical. In networking, jitter cleaners keeps Ethernet signals aligned so packet errors don't creep in at 100 or 400 gig per second. In wireless, they ensure base stations stay locked to spectrum allocations, and in data centers, they sit in the clock path for PCIe in memory, making sure those signal eyes determine how stable your data is on high-speed serial links. You can kind of think of a jitter cleaner basically like a clock refinery. The input comes in rough, polluted with noise, and the output leaves smooth and disciplined. Without jitter cleaners, modern high-speed links wouldn't have timing margin they need to work. So now we're almost at the end of this diagram, but we still have a couple to go. If you're keeping track, we're kind of getting further and further away from the actual thing that vibrates. This is what happens when you want to go fast, but then you need to go fast at scale. So far, we've been talking about keeping time inside a single system, but a network synchronizer is what you need for multiple systems to stay aligned. In telecom and data centers, equipment isn't just running on its own internal clock. It has to line up with every other box in the chain, whether that's a 5G base station handling calls across a city, or a set of switches pushing 400 gig Ethernet across a backplane. If one piece drifts out of sync, packets get dropped, links flap, executives flap more, and the stock flip-flaps, and services fail. A network synchronizer is built to lock onto an external timing source, usually a high stability reference like a GPS or an atomic clock. And if you've been following this channel for a long time, we actually did a video on the timing card from Meta back in 2022. Inside that was a rubidium nuclear clock designed for parts per trillion accuracy across data centers across a continent. That high stability reference distributes the discipline clock through the system. The synchronizer in this case has to handle multiple references, switch between them if one fails, and provide holdover performance if all the external signals disappear. Now, I've said it before, but holdover is the ability to keep running on the internal oscillator while staying close enough to the specifications of the external when the links collapse. What makes synchronizers unique is that they bridge local hardware with global time. They're the devices that ensure a packet sent from Tokyo arrives with the same notion of now as one from Frankfurt. That consistency is what allows protocols to scale, networks to interoperate, and the global infrastructure to behave like a single system. Just don't ask me to explain a leap smear, but that applies too. Now, as we've gone further and further up this diagram, I've kind of veered away from saying MEMS a lot, but one of the key attributes to MEMS is configurability and control. We sometimes laugh at the concept of the digitalization of things, but in timing, that matters when you're going from shiny vibrating rocks to precision vibrating microstructures. The point is that after booting, these timing circuits need to be controlled, and it's the granularity of control that matters. How fast you can turn a core on or off in a modern CPU, for example. Now, software in this case adds adaptability. For the big systems, it chooses which reference clock to trust when multiple are available. It decides how to distribute clocks when GPU use patterns shift in a data center. It can apply policies for when power needs to be saved or when priority links need the cleanest signal. It can monitor hardware health in real time and reconfigure the system if a source degrades. One of the most practical benefits is extending the ability for the clock to hold its device when the reference disappears. Again, this is a third mention of holdover at this point, but a well-designed synchronizer with embedded software can predict oscillator drift, correct for temperature, and dynamically calibrate against known baselines. This effectively doubles how long a system can stay within spec when that external reference drops out. For a telecom switch or a data center spine, or something out in the field that somebody might have dug up because they wanted to sell the copper in the cable, that added margin can mean the difference between seamless continuity and drop service when the cable eventually gets reconnected. In that sense, software doesn't replace the precision hardware we've talked about, it just makes it more configurable and extends the benefits. It makes the most of the physics, pushing reliability and coherence beyond what the raw components could guarantee on their own. Now, this is a long video, right? There's a lot of info, and in no way am I a timing expert. But when you sit in front of your word processor or gaming rig day in and day out, watching frames go by, it's sometimes easy to forget just what's going on in the fancy sand we somehow taught to think. Resonator this, oscillator that, buffering and jitter cleaning, all while I'm trying to teach a teenager what it means to get pwned in Mario Kart. The landscape of advanced precision timing is one that's going to pass a lot of us by. I said some numbers at the beginning, but the reports I've seen put the addressable market revenue here at $11 billion by 2027. A lot of that is being driven by AI, but also fundamental backbone infrastructure where the trade-off between cheap quartz and reliable MEMS is a debate going on in a lot of chip design companies for every generation. As we get faster, and as we need more accurate tick-tocks for the tokens or the 6Gs, that decision might get easier and easier. Many thanks for SciTime for sponsoring this video. They are the market leader today in MEMS, and I've got an interview update lined up with their CEO soon. So if you have any questions, please do leave them down in the comments. If you didn't see the previous interview, check out the links on your screen now.